we have not been yet in the format of the annex because we joined later, and also we have been really concentrating on intervention potentially possible on a large scale without a lot of energy, without a lot of investment in terms of cost. So we'll present quickly three case. One is natural ventilation in the case of a low affordable housing where we have helped heavily in the design, and then the low energy ventilative cooling and tested in a building also in terms of the aerolic concept, and then the natural ventilation with and without external shading. So maybe just so I'm the leader of the building energy efficiency project for the Swiss component, and then my colleague from Green Tech in India are the partner with whom I work. So here we have been designing, I would say we have been contributing essentially to the design of a 1200 flat complex in Rajkot, and we have done a study there about the actual comfort condition, given the fact that in India almost 90% of the people do not have any active cooling. So we have developed this design with the idea that people will not have cooling at least for the next decade or even 2 decades, which is the trend is going for higher number of AC, but still low income people are generally not able. So we wanted to demonstrate the natural ventilation efficacy to stay the temperature much below the outdoor temperature compared to the internal temperature. So few feature, it's a very low heat gain building envelope in terms that it has aerated air concrete blocks, which a U value of about 0.7. It has a very low window to wall ratio. And the thing also specific we did was to use the CO2 as a tracer gas, because this is very cheap, and we tested it and it worked well, provided you have a guard. So we did first, I go fast on this, this is more like the methodology of which was followed. And then you can see here the choice. This is the complex of 1200 dwellings, and you see here the place where this flat is. You see here more in detail. And there is one thing which is important, is that you see there are recesses at some point and some place, and you will see that it has an influence on the airflow. So to plan the measurement and have not so many, we didn't have the many sensors. It's too expensive for such projects. So we have actually used CFD to determine where the most average representative location would be for temperature and CO2 sensors. And the thing which is interesting is this recess, you see that when the wind is coming in this direction, actually it enters in the building on the let's say lower part of the wind after, and goes back through the window again. It's an interest, even though there is hardly any bypass, because there is enough distance between the two. Then we did so. To use tracer gas as a CO2, it's never done usually, but we have made the system with a guarded zone, so that the whatever relate to acquisition you could enter in that and does not generate CO2 by human breathing. And so we did also a check on the CO2 ppm measurement with a constant source, and then compared with the decay model, and could see that we had a good measurement. Then you can see here the results over 1 week. There are more weeks, but this is one week, which is quite interesting as an example. So you can see that the ambient dry bulb goes up to 41. It's between 38 and 41 during this week. So it's not maybe the hottest, but still you can see the difference. So what you can see that in green, you have the temperature in the bedroom. This is the operative temperature. And you can see that we are keeping below 33. And even when the temperature reaches 40, we are still with a difference, we can say, of about 7 degrees. So we did the calculation with the with the IMAC, Indian Adaptive Thermal Comfort Model, which has been developed recently by CEPT University, the CARPSE group. And we have used their algorithm to define the acceptability in the Indian context. So we can see that we are almost in the 90% acceptability. People, of course, have ceiling fans. This is part, everybody has ceiling fan in this kind of flat. That's the only thing they have normally. And so with 30 up to 33 degree, it is, let's say, what we could say in India, we consider that as acceptable, but in reality, we can say it's bearable maybe, but still people accept and live like this. And the first result on this building is that we have been able to demonstrate that with a proper design of building, we can keep 7 degrees below the peak outside if we have a proper natural ventilation and low window to well ratio, etc. tool of the design. And then we can see that this results in a significant increase in comfortable hours over the year, and also in the reduction of the acceleration of the air conditioning. The second case is when you don't have sufficient wind, because you have many projects where they are so near and let's say facing the wind and not letting the wind in between the building behind. So we know that, for instance, Pierre Heiselberg had demonstrated also with some study that 12 air change is something we should reach if we really want to have a higher heat exchange coefficient for cooling at night. So the idea was how to make a balanced system without any mechanical control, to have with one central fan at top of a central shaft, drawing air with about 10% difference between 7 floors in this case. And so for that, we use CFD, computational fluid dynamic, to test different concepts. Then we make a mock-up model testing for the balanced system, and then a testing in real scale. And we used, let's say, relatively high performance fans, and I'll show you later. So you can see here in CFD, this is inside the building when the air has entered through the facade. Now it is the entrance into the toilet, for example. And then you have the air entering into the toilet. And then you can see here, this is the balanced system, which let the air goes into the central shaft. You see the shaft is at 26 Pascal negative pressure approximately. And so after that, once we have the model, then we have made a real mock-up model in which we have bring the air so that we have a differential pressure of 30 Pascal, and we got about 450 or 500 cubic meter an hour for each exhaust. So we have 2 per flat. So it gives, in theory, after something like almost 1,000 cubic meter an hour for small flats. The flats are only 28 meter square, 28 square meter. So here you see a view of the system. You see this is from the bottom looking upwards. You can see these openings which are here, 4 per floor. You can see 2 for each flat. So you have 14 flats. And then you can see here the CFD model. We have reproduced the same thing first with the CFD, and then it has been constructed. And you see here this exhaust, which are downward directed to avoid that anything could enter into it, because if people are throwing things, and also avoiding that animals or things can come in. And then you can see here that's why it's blowing down. And then if you look now at the result, so this is the principle of the system, and that means it enters through the windows on the facade, and then at top you have this calibrated exhaust. And then you can see that we have, for the test, we have developed a special system with a long duct, so that we can measure the total flow at the end of this duct. So you can see this is the CFD model again, and this is then the real model. You can see the ladder where we have been taking the measurement for the velocity to have a good accuracy. And you can see here the high performance fans we took from a German manufacturer with quite high efficiency to test actually how much we could expect. So the results is that we have the airflow is approximately the same or even a little bit higher than the design, and we have consistent between 12 and 15 air change in the flat, in all the flats which are around this, and then you can see here the comparison. This is the design where we had minus 30 Pascal with the CFD and the value, which was 14,000 cubic meter an hour. Actually measured, we have reached at the total measurement at the end of this duct I showed you before, 15,500 cubic meter an hour, and going through the exhaust of the flat by sampling, because it takes a lot of time to measure all, we could see that it's consistent. So the conclusion is that it is possible to make a very low energy ventilative cooling very simple in terms of technology. We have shown in real scale the hydraulic performance of the system with a very low negative pressure and well-designed, let's say, resistance for the exhaust. With high performance fan, we are able to bring 12-15 air change at night with 1 watt per square meter approximately. Then there is an additional thing that we unluckily did not get sufficient time and constraints, but we could test quickly when you add an evap cooling pad on one of the window, and then you make it run. We could see that it was significantly good, and it was not really affecting the balance of the system. That means if some people had it or not, we could see that the variation was less than 20% between the different flats because they have a low pressure. So this system should be further developed and tested also. And then here you see the results, which are just the metric. So I think then the third thing was to see whether with and without external shading, because in India there are very few people using external shading. There are now few in the high-end Pentium house, and that's not at all yet in the market, and people are not believing much in that. So we had to make a demonstration. We are now that will be used at the national level with a policy paper. And then what we did is selection of 2 adjacent flats. That means one on top of each other, 10th and 11th floor. And then we have checked the initial condition and then did actual, and then we got the result. So here you see the three towers like this. So we took one of them, and we took the west facade with 1 room, typically. And you see this is the typical test room that has been in detail monitored with a lot of sensor equipment. And here we did the first test to be able to compare whether the 2 rooms were really behaving the same without anything, without shading, just free floating. So we could see after a few days that we got a very good matching between the 2, so we could be sure that the comparison is fair or is, let's say, consistent. And then when we look at the results, so we have one which doesn't have, that's the red curve is actually the temperature in the room. The dark, the dotted curve is the outdoor temperature. So this week was quite a dynamic week in a sense. It went up from 35 up to 39 degree. It's not completely fully, but we can see the blue is the one which has the shading with the SHGC of approximately 18% total for the Windows system. And you can see that on the hot day or hot and clear days, we get something like 3.5 degree difference in the peak. That means with the external shading, with everything being similar, and that means same strategy of natural ventilation, same strategy of closing the windows during the day when there is the sun, we are getting 4 degree almost difference, especially here. You see when one day is really clear. You see in yellow, this is the solar radiation incident, and the diffuse is then the gray one behind. And then you can see that we really actually get something between 3 and 4 degree almost of reduction, which means a lot of reduction in duration compared, because this is only the peak. If we do now by simulation we have done, we will produce soon a report on this, how many hours are per year your reduction. It's a very significant reduction of the duration of discomfort hours. And also, of course, this building is maybe less performant in terms of passive strategy than the low affordable housing of the case one, but we can see that this confirms the relevance of external movable shading system in hot Indian climates, and we are now preparing for the Indian government a policy paper to make to try to get also more suppliers and manufacturers of windows trying to join so that they start developing the market for that. So this is my I have completed now the presentation.